Hello there! Today we will explore another crucial force that comes into effect when we start modifying an object's shape. This particular force steadfastly opposes any alterations to the object's shape. You may often come across this force in daily life, like when you stretch a rubber band or a spring. In such instances, you can feel the object resisting your attempts to deform it. This force, which emerges within the object, impeding its deformation, is known as the force of elasticity. But what causes this force to arise? It is a result of the intermolecular interactions taking place within the object. Each molecule is surrounded by neighboring molecules with which it interacts. These interactions, whether they involve extension or repulsion, start to reveal themselves when we deform the object. Essentially, deforming the object directly affects the distance between these molecules, and naturally they resist this change. When we compress the object, the distance between the molecules decreases, leading to repulsive forces that strive to bring them back to their original positions. On the other hand, when we stretch the object, the distance between the molecules increases, creating an additional force of attraction. These molecules work collectively to counteract the external force and strive to restore the object to its initial state. All of this falls within the realm of an electromagnetic phenomenon, as it involves the interplay of electromagnetic forces within the object. So we can confidently describe the force of elasticity as electromagnetic in nature. Now we may wonder what laws govern this force. To explore this further, let's conduct a quick experiment and consider a specific situation. Suppose we have a certain spring which, in a free state, that is, without any load, has some length which we will call as L0, and under its own weight it can stretch if we are talking about some real situations, but in this case we will neglect the spring's own mass and say that it has no deformation in this case. This is its state of equilibrium. What happens if we suspend some weight from this spring? Clearly, under the weight of that weight, the spring will start to lengthen. And eventually its length will become longer by some value x. In this case, this value is called absolute deformation. That is, it directly shows how much the length of this spring has changed. That is, if we now consider the change in length of a given spring, x is the difference between the final value and the initial value of the length of that spring. The absolute strain will then occur in both cases, when we stretch the spring or conversely compress it. In either case, it will show how much the length of the given spring has changed. If we double this action, which in this case is exerted on this spring, what happens? If we now hang two of these weights, two such weights, in this case we get an increase of the same value of x from the length of this spring. This shows that depending on the applied force will depend on the force that occurs in this spring. That is, its length will begin to grow in proportion to the applied force. Actually, this is the main law that describes elastic deformations. This law is called Hooke's law and can be mathematically described in this way. That is, the force of elasticity is a kind of direct dependence on the absolute deformation of this object. What is the coefficient of proportionality between the force and the given elongation? Naturally, it is a property of the spring itself, that is, its characteristic, which depends on what kind of spring we have taken, how long it is, how thick it is in terms of its cross-section, what materials it is made of. That is, all of this will affect its final parameter, which is called the stiffness of this spring, denoted by the letter K. And in this law, of course, we must still put a minus sign, saying that the force of elasticity, which will act on this system or on the spring itself, it will be directed against this deformation vertically upwards. Well, accordingly, the total weight of this system, let's denote it that way, will be directed vertically downward. And as a result of balancing these two forces, the system will be in equilibrium, and thus we can experimentally find let us say, the parameter of this spring if we know what weight we have suspended here. If we consider this situation from the point of view of the law, let us write it down. This is the exactly Hooke's law. The application of this law is very widely used in problems. That is, we can say that this force occurs not only in springs, and we clearly see this deformation, but it also occurs in other cases when this deformation is not clearly visible, but we can clearly say that it is present there. Suppose we consider some body which is suspended on some rope. That is, the rope is no longer a spring, but nevertheless it also undergoes deformation when we suspend some weight from this rope. And we can say unambiguously that it also undergoes a certain elongation under the action of this load, and a certain elastic force appears in it too. The only point is that in this situation we denote this force as a tension force of this string. We denote it by the letter T, tension. In essence, it is the same elastic force, but we describe it a little differently here. That is, we do not consider the elongation of the rope or thread itself. Our task is simply to show the presence of this force which will keep this object from falling. This is the most important effect that will occur in this situation. But we must understand where this force comes from and how it will be directed, because then, when solving the problem, naturally we will use this phenomenon to describe the state of this object. Here we see that, of course, the condition must be fulfilled that the weight of this object will be compensated by the tension of the thread, and then the body will be in balance. We can explore slightly more complex scenarios, such as when threads are not positioned vertically. For instance, imagine a situation where a thread is secured in a horizontal state. By considering these variations, we can delve deeper into the subject matter. That is stretched between some 2 points, and we suspend an object from the center of this thread. That is, at this point we suspend some body. What will happen in this situation? Naturally, this body, due to its weight, starts to change the shape of this construction as a whole, and as a result we can draw that the situation has changed, and the geometry of the thread itself has also changed. That is, in this case, relative to its initial position, which the thread occupied horizontally. Now we have it occupies this position, that is, the middle will sag under the action of this object. And now if we talk about the forces that will work in this situation, we realize that we have the weight of the object that starts to act on the rope itself, and the emerging tension forces inside the rope will compensate for the weight that appears. To compensate for that weight, in this case there is a certain angle of deviation of the rope from the initial position, denoted by the letter theta. And here we have a more complicated situation because we have to consider the balance of forces along the coordinate axis, because we see that there are certain angles that this tension force makes in relation to the standard axis. And we can look at, let's say, the components of the tension force on the two axes, which are exactly what will be responsible for the balance of this system. That is, there are Tx components and there are Tu components. And we can see that each of these two tension forces, and they are the same in modulus because it is the same thread, these horizontal components will compensate each other. This will tell us that the system is not moving, neither to the left nor to the right. And vertically we see that the weight is compensated by these two vertical projections, and then the equation of equilibrium will look like the weight of this object is twice the projection on the vertical axis. That is, from each force there is its own projection which will make up together the total force that will balance this system. Well, each projection we will be able to write through the corresponding angle, that is, if the angle T appears between the original position of the thread and the new position, it appears in this triangle and here, and then it will be an opposing cathetus, that is, we will paint it as 2 T sin theta. As an example, we can consider such situations and just the equilibrium of such objects with the help of threads, with the help of solid supports, with the help of springs we can describe by the appeared force of elasticity. And of course Newton's laws will work here too, because the basis of balance is in the first law of Newton. This is goodbye. We will see you now at the lessons of practice, where we will apply these laws. See you all soon. Goodbye.